So we're steering slowly towards the end, but please bear with us. There is still, I believe, a very interesting topic from Thomas. And yeah, Thomas, welcome to the stage.
So good afternoon, everyone. Some of you may know me or not, but you'll see on the next slide. I'm currently a principal architect at NVIDIA through the Mellanox acquisition, which was why Pascal was pointing to me when there were questions about ConnectX NICs. Today's talk is about time transfer requirements in the network and data center. So there's going to be some for the layer 1 to 3 folks, and then there'll be some from the layer 7 and upwards in terms of why do I care about this at both ends of the spectrum. So first of all, what is this topic not about, or a history rundown for those who've been around for quite some time? This is not my presentation from SwiNOG 1 on peering policies, nor is it about designing and deploying VoIP networks at SwiNOG 5. Nevertheless, it's still not about Metro Ethernet at SwiNOG 8 or the IPTV broadband of SwiNOG 12. There's a theme here. Video for network engineers, what's relevant, SwiNOG 17. These are all in the archives if ever one day you want to go and look at it. What happened in the 2000 to 2010 decade at SwiNOG 20, maybe I should do an update on that one. And AMT automatic multicast at SwiNOG 22. But since I've not presented, so you know, what have I been up to for the last decade for those who would be interested? Well, today's presentation is about high precision, and I put in quote marks because everyone's definition of what is accurate/precise is different, and we'll talk about it in the presentation. Time transfer across networks. I'm going to focus specifically on a IEEE standard called 1588 PTP, and you'll understand why, and there'll be the whole discussion of, you know, why do I even care and why is it important? Basically, for the last decade, I've been living in a nanosecond world, which is the level of accuracy for the applications I've been involved with. I'll break it down into 3 parts. Use cases, i.e., you know, why do I care? Some timing 101, because not everybody will be familiar with some of the concepts, I assume, so I just want to set the record for everybody. And then I'll close on something that's been going on in OCP, so the Open Compute project. There's a group called TAP, Time Appliance Project, which has created a specific profile for time transfer related to data centers. So timing is actually used in many different industries. Okay, so you have specific requirements, and I'm just going to illustrate a few of them in order to explain the purpose. So this is a vertical I've been working on for over a decade. This is what led me down the rabbit hole of precision time. The media industry, specifically the media production industry, so TV studios, has moved from a legacy technology that they had to IP. And in order to synchronize audio and video, you need some form of clock mechanism that is precise enough so that all your cameras and all your microphones are synchronized. So that's been ongoing for a decade, and there are projects around the world, including Switzerland, which include this technology. But that's not today's discussion. Telco, 5G, frontal radio access deaggregation, separating the radio unit from the DU, is another area where timing has been around, well, more precisely recently for these kinds of applications, and historically from the days of TDM, which has been carried over to IP and so on and so forth. Finance, high-frequency trading specifically, and also the auditing of logs and everything else to make sure that there is no inside trading or trading didn't occur on somebody's feed before somebody else's feed requires time precision. By the way, all these 3 use cases have different definitions of what time accuracy and precision happens to be in terms of, do I care about this on a millisecond, microsecond range, nanosecond range, picosecond range, should you wish? So today's topic is obviously about the last one, which is going to be the data center. So I pulled this quote from a, when I say well-known paper, a paper that is well-known in the industry and builds on top of work that's been done by many people over the last decade. But this is the I think it's the abstract, first sentence in the abstract or first sentence in the paper. Nanosecond level clock synchronization can be an enabler of a new spectrum of timing and delay critical applications in data center. The paper is co-authored by a bunch of folks at Google and Stanford. And this was back in 2018, and it builds on top of existing technology that had been deployed typically for the likes of Google Spanner, which is a large-scale database replication system. So why am I talking about Google and large-scale replications? It's not for everybody, but you'll understand as we go through the presentations that there are many other use cases. So what you want to do is you want to provide a reliable time synchronization model across the data center, something that's unified. They can provide sort of timing as a service, should you wish to, depending on if it's your own infrastructure or you're providing it to customers. And there are mechanisms to do that. The next two bullets are the important ones. First of all, it'll enable a new set of applications, which I'll talk about in the next slide, but it also can improve existing applications. And it's one of those cases of you don't know what you don't know until you understand the technology, both as a software engineer and what are the benefits, also from a network engineer point of view as to what are the benefits for your own infrastructure or deploying it. The talk, as I said, is based around something called PTP, which is a standard that originally came out in 2002, was majorly revised in 2008, and was updated in 2019. And the main goal, as it says here, is that you should be able to reach an accuracy that's 2 to 3 orders of magnitude better than what you get with your typical NTP infrastructure. Again, if you're just wanting to log stuff because you need to know what time somebody checked in or whatever, you may not need this. But if you need something more granular or you're trying to do root cause analysis, it may be beneficial. By the way, I mentioned picoseconds before. There is a bunch of corner cases, specifically in some scientific applications, where we're looking more around 250 picosecond accuracy, or even better than that, for very specific applications. Again, it's not the run-of-the-mill. It requires very specific designs, but it is relevant to some parts of the industry. All built on the same standard, but for different requirements. So again, you'll say another Google case. These are links to papers. So Spanner is the database, TrueTime is their timing model, and the CAP theorem, which claims that you can only have 2 of the 3, consistency, availability, or partition tolerance. And through the improvement in timing accuracy, you actually get very close, I say very close, to having all 3 of them. So a bunch of use cases. Distributed database is actually the hot one. So I talked about Google Spanner, but others also operate large databases. There are also open source implementations. You'd think of things like CockroachDB or others that actually benefit from using timing when you're doing global database replications. So between data centers, between zones or whatever. Maybe a managed service for a customer, a service internally. It really depends on what you're doing. One-way delay measurement is typically another one that it can be useful. Instead of having measurements around RTTs, you want to see how things operate between A and B. But if you want it to be precise enough to actually understand if there is something very specific in a given path or a change in that baseline, the more accurate host A and host B are when you do your one-way delay measurement, obviously, the closer you get to a perfect situation of understanding what has changed. And it might be at a millisecond, microsecond, nanosecond level, depending on the technology, how you deploy it, and what you're using. Network and host-based telemetry. There are a bunch of applications where you're looking now more at, buffer contentions, microbursts, things like that, and these can be very short-lived. I've just linked to a bunch of tools that Meta has. They've published papers and they've open-sourced it, the software, and they have means to be able to include precision time as part of their modeling. Another one, which is actually built on a tool from NVIDIA called Nsight Systems, which allows you to do system-wide performance analysis. Okay, I mean, I'm using this as an illustration case, but the idea is as systems get more and more distributed, multi-host, multi-node, you want to be able to do more precise root cause analysis. Now, this is when you're actually looking into the details of interactions, such as processes between CPUs or CPU-GPU interaction, for example, or you're looking at how the flow is operating between multiple nodes. So I'm talking workflows here. Then you can bring it down to network flows, depending on where you sit in the stack. It is often used also for interrupts, wait states environments. You actually want to understand where you're wasting cycles so you can improve your performance. And last but not least, there's always a blob about security, because if you can improve your logging, if you can improve the timeline in which events occurred, it will also help you maybe with another set of root cause analysis on what occurred during a breach, or I don't know, a BGP peer that went AWOL or whatever else it may be. So the whole idea here is saying there is technology out there that allows you to improve timing performance, which actually exists, and we'll talk about where it sits in terms of the industry afterwards. But I'm going to focus, for the purpose of time, specifically on one use case, which is the distributed database, because it's actually a hot topic in many environments. So why do you care? It doesn't apply to every single database model, let's be honest, okay? So the important thing is what you're trying to do is you want to guarantee that a transaction, okay, is committed at time T1, your write operation, before another transaction that occurs at T2, such as a read operation, occurs. Because otherwise, you'd be reading stale information before it gets written. And that's typically what could happen in a distributed database model. I'm also keeping this to a quite high-level concept. Like everything, mileage varies, but this is what we're talking about. So in order to avoid that kind of environment, you want to align the clocks on all your nodes in the distributed system to ensure that they will display the same time. Okay, so the concept of the accuracy of time comes into play here. And what you're trying to work on is something that we call epsilon, i.e. the window of uncertainty, which ultimately means I am looking at if the error between A and B is within a certain range, and usually it's something like the RTT, I know that I should be okay in terms of the read versus the write. So what you're trying to do is you're trying to enable the ordering of the operations here, okay? But that's not always sufficient. So a lot of these databases will use what we call strict serializability, which uses what we call a two-phase commit. So you're actually locking a resource, and then you're making sure that everybody has that resource locked before it actually proceeds to the next stage. And there's an analogy that has been done more than once around this sort of model, where you actually say it's like if you're trying to do a reservation for a trip and you want a hotel and a flight and, I don't know, rent a car or whatever. You want to make sure that all those resources are locked, i.e. I can have all the flights, the segments, the hotel rooms and everything else before I commit, i.e. before I make the transaction. It's the same sort of model if you think in a banking situation where if you want your bank to give you a certain amount of money, they need to lock that before the transaction occurs to make sure that that money, even though it's a digital transaction, actually exists. So this is, if you want, the high-level concept of a two-phase commit. So the ordering becomes extremely important in here. And obviously, you want to avoid as much as possible any clock skew in order to guarantee that between the machines, you have this linearizability of the actual data. So to illustrate this, I'm going to pull something from Meta, or formerly known as Facebook, where they actually deploy this at scale in their environment. This was from a blog post that they did, references at the bottom. So this is exactly the commit wait stage. You're looking at the bottom right where there's the read. That's the current state. Okay, so this is the commit wait as you're going to move along the process. And the next one is now, can't read it on my screen, unfortunately, the read that is blocked. So that's, for the details, you can go and look at how they've implemented it. But my point is, it exists in different states. I could have pulled up some slides from CockroachDB or other database systems that actually use it, but this is just to illustrate. So typically when you're doing this across data centers, across regions, the further you get, the more you need to create this sort of wormhole between your data sets so that they're actually co-timed and that the transactions are done in the right order. So what happens next usually is people ask me, so why isn't NTP good enough? So I could do a long explanation, and it's not about NTP versus PTP, because each one has their own use cases, but it depends the accuracy you're trying to achieve. So I thought I'd take yet another picture, which I also stole from the same blog entry from Facebook Meta. On the left-hand side, they've deployed Precision Time Protocol, and the commit wait time latency is drastically reduced compared to the right-hand side of this slide, which is using NTP. So they have a significant performance gain due to shortening the commit wait time for the different transactions. So it's a way of improving the overall performance of your system also. So that's about the use cases and one specific one, which was the database one. Now, okay, you understand that timing can be useful and that there's this protocol called PTP. So let's dive into the next level. Timing 101, to try and get everybody on the same page. What are we talking about when we talk about clock sync? So this is a high-level representation, obviously. The black line is the ideal sync that you would achieve if everything was perfect in a perfect world and aligned down to, the atomic level. You would have this server time and client time, i.e. the time that is being sent from your server transferred to the client would always be in sync and would be 100%, okay? The reality is you are actually doing a time transfer and you're disciplining a local clock. And through the messages that are being used, it being NTP or PTP or some other means, you're actually disciplining the client itself based from that source clock. And there are different models using multiple sources. There are different models in terms of redundancy. But that's the general concept, compared to a free-running client, which over time, no matter how good your oscillator may be, we'll exclude a couple of cesium clocks, which you most likely don't run in your end hosts, you're free-running over time, whatever that time be, if it's a minute, an hour, a day, a year, a month, or the lifetime of humanity, will drift, obviously. The other concept is accuracy. There's precision and accuracy, and it's dependent on two things. So if we look at the right-hand side of the slide, there is, I'm not accurate, I've got low precision. That's usually cheap implementation or cheaper implementation. Accurate, but low precision. So I'm more or less in the bullseye, but in the region of the bullseye, but without being actually in the center. At bottom left, I am not accurate, but I'm highly precise. Every single time I'm hitting it at the same point. Some applications just need that. They just want the precision, okay? But the accuracy might not be important. There are given applications. But obviously, you're trying to aim for the accurate and highly precise. Again, if you take the dartboard, you could turn the circles into whatever scale you want it to be, milliseconds, microseconds, nanoseconds, picoseconds. But it is dependent on a certain number of contextual information. So first of all, what is the time-stamping resolution that you're able to use? Do you have a time-stamper that's running at, 100 nanoseconds, 10 nanoseconds, 2 nanoseconds? What's the local oscillator quality? And how is it aged? And what's the temperature? And do you have any temperature drift? So all these exist in terms of specification. I'm excluding all the bugs that exist in real-time clocks and implementations on different generations of motherboards and so on and so forth. That's a whole other realm. Network-wise, packet delay variation, that always comes into play. Usually these are symmetrical environments in which you're operating, so anything that causes PDV, if not accounted for or not designed properly into the network, will cause variation. Variation equals jitter. Jitter equals lower performance in your time transfer. Time-aware network devices, we'll talk about it afterwards, but today you have routers or routers and switches that are time-aware and will be able to forward those messages. I'll talk about it on the next slide. Asymmetries, different paths, upstream, downstream. And these things can be as subtle as, RX versus TX fiber is not the same length. It is created in asymmetry. It doesn't have to actually be a packet going through one path and another. Again, it depends on what you're doing. And the highly asymmetric network loading is the next one, which will cause you a certain number of issues because, again, depending on if the packets are being queued because they're not using time-aware protocols, and that the switches are not configured properly, you would end up having issues related to packets are going faster in one direction than the other. And that creates another set of skew. Last but not least, message rates. You can use low message rates, but you can also use higher message rates. Different industries have different requirements for that. So next in the Timing 101 section, we're going to go from the left to the right. On the left, I have some form of reference clock. The most common thing is GNSS, aka what people will call GPS, which in this case is the Global Navigation Satellite System. So we're being agnostic of if it's a European, a US, a Chinese, or any other satellite system that provides clocking. The humorous version is I could have a hamster in a cage at a wheel running at a very precise speed, which would also be a way of providing a reference clock. That reference clock gets inputted into what we call a grandmaster, okay, which is going to be the source of time. Replicate these, make them redundant, have multiple of them. There's a whole protocol around how you elect who is the current grandmaster based on current reference clock performance. The PTP traffic goes first downstream. It may or may not traverse what we call a boundary clock. The boundary clock, as its name implies, will terminate the timing traffic, i.e. the PTP traffic. It will discipline its own clock, usually in the process, but not always. And then it will send the traffic back downstream, so it regenerates the PTP message. So it terminates the session and recreates it. And then you may or may not, again, have transparent clocks, which, as its name implies, is transparent. In this case, it doesn't do anything to the message, but what it does, it updates what we call a correction field, which is the residency time that it took for the packet from ingress to egress. So whatever amount of nanoseconds it took to cross the switch, that gets added to a header, which will help compensate on the endpoint for any time delays. And at the end of the chain, we have what is known as slave, or in modern language, follower. And then you recover the clock from that. So you're disciplining a hardware clock, a PTP hardware clock in there. You recover it, and then obviously this is sitting in a server, so on a NIC. And then you will do a time transfer, most likely, to the real-time clock of the host, or not. Some applications read directly from the PTP hardware clock. And in the end, the whole purpose of this is so an application or a set of applications will actually use that time. So the way it works is, I said there was a leader / grandmaster that actually sends what we call a sync message at a certain point in time. It obviously takes time for that message to propagate through the links, depending on serialization, speed, length of cables, whatever. And a bunch of devices that are listening, followers, will receive it at another point in time, few nanoseconds, milliseconds later, most likely milliseconds. And then there's the reverse path, which is called the delay request, okay? And the delay request goes back up to the source and will say, hey, I now need the timestamp between when I sent it and when you received it. But now that timestamp is sitting on the leader. So I need to get it back to the endpoint, the follower, which is actually computing the time. So I have a delay response that works here, okay? So using these different messages, and by the way, the sync message can be sent unicast, multicast, v4, v6, layer 2. It depends on the implementations. The delay response is unicast or multicast, depending on the architectures. And the same for the delay request, obviously. Using this, I can build these pretty simple yet useful equations, which is calculating the offset I have from my master / leader and the delay. Okay, so now we have a notion of how far behind I am and what is my current offset. And with this, you have the basis of a time transfer between a source or a leader and a follower. This is a full stack of all the things that come into play once you're like, oh, this is a good idea. So from the bottom, hardware timestamp resolution, different network cards, different switches, different routers will implement hardware timestamping with different degrees of accuracy. It is actually very common on literally every single piece of silicon that's being pushed out these days. But most people don't even know about it because you've never had to use it. Jitter under load is one of the main concerns in that case, and depends on the quality of implementation. It's like saying I have a car. I could have a car for rally, Formula 1, or going shopping, or for my weekend ride in the mountains. They're all cars, but they all serve different purposes and have different performances. There are problems related to operating system noise and CPU interrupts. And now you think I'm telling you it's all really ugly, but actually this is the full stack of things you want to know about, as opposed to me making it all nice and fluffy. Depending on how you're operating and the level of accuracy you're looking, you need NUMA alignments between the CPU and where the processor is running, that it's on the same NIC that's doing the timestamp and the memory that's been allocated, just to make sure that you're not wasting time / jitter in that environment. Server configuration, that's in the PTP stack itself. The operating system timing capabilities. Linux, first-class citizen, works really well. Windows, meh. There you've got a whole bunch of problems, and the support that exists in the latest versions of Windows is still extremely limited. They do PTP. They do, if you love going into the registry and typing stuff in. But it is extremely specifically scoped for a target set of customers that requested it, and is why Microsoft inserted it into their OS or OSs. And at the top, we have the PTP stack itself, which is disciplining, getting all the messages through the stack, has a server configuration, is disciplining the PTP hardware clock I mentioned before. So then you'll say, well, do I really need hardware time stamping? Do I need these latest generation or new hardware or whatever? Well, when the PTP spec came out originally in 2002, there was literally no hardware timestamping because it was all new. And performance-wise, there were also a bunch of problems. So software timestamping was very common in the early days. But you're not going to get the high-level accuracy. You'd be closer, most likely, to the NTP, or maybe a bit better, due to system noise, latency, scheduling, whatever else is going on with those packets as they go all the way up to the CPU. So you can see on the left side at the bottom, you've got the interface, the PHY, the Mac, the ASIC, the operating system, and everything timestamping and PTP and clocking happens all at the top of the stack. As opposed to the right side of the slide where we talk about hardware timestamping, and here we want to pull all the timestamps as close as possible to the physical layer, okay? Which means that in modern implementations, you can get sub 10 nanoseconds for no extra cost, depending on the type of hardware you're getting. If you're getting a home grade 50 Swiss franc NIC, you might not be achieving that. If you're getting something that's more data center class driven, you most likely will. So as you can see, the timestamping now occurs more at the PHY layer, and then it is read there from there, and then it will go to the PTP stack sitting at the top layer, of course. So the mandatory CLI screenshot, this is just to illustrate two different types of NICs. Obviously, I work for NVIDIA, so it's going to be a ConnectX-7 and a 60X, which are the latest generations. And by the way, for the 60X, in this case, I put this one in because not only it supports timestamping, but it can run as the master / grandmaster I mentioned before, because there are boards now that have GNSS connectivity in order to provide a reference clock to your system. So what you're looking for from a Linux point of view in your Ether tool is simply what are the timestamping capabilities of your NIC. So you want hardware transmit, hardware receive. There is a PTP hardware clock, the PHC I talked about. You can have multiple instances. This one is 2 and not 0 because I've got other boards in this machine. And these are the main criteria you're looking for in terms of your capabilities. Obviously, you would like to have also the hardware transmit and receive timestamp modes and filtering. On the right side of the slide is just a Gaussian distribution of a load testing that was running. I think it ran for about 3 hours, if I remember that one, just looking at what is the sampling of the offset that you would have over that period. And the scale is in nanoseconds. So, max was plus minus 20, 25 nanoseconds, which for literally most of the applications, at least the ones I mentioned before, for the data center space is more than sufficient. So I mentioned earlier that you have different profiles, or more to the point, you've got different industries that have different requirements. And those requirements are then built into what they call profiles. So you take the 1588 specification, and you build into profiles for the industry. So I mentioned telecom, 5G, deaggregation of the radio access network. There are a bunch of ITUT specs for that. And it's ongoing, and those are following things in that space. I actively work in that space. Obviously, I'm following it. There's a lot of knowledge from the last 20, 30 years of TDM that went into designing these specifications. And in my opinion, they're some of the strongest and well-designed time transfer specifications. There are other industries, and I spent also quite a few years working in the professional audio video, as I mentioned before, in something called SEMT, Society of Motion Pictures and Television Engineers, to define or help them define their PTP profile for the sync between the audio and video sources. And other markets such as power substations today can actually be synchronized using 1588. Then there's the AVB spec, which some of you may be familiar with because we see it more in, I would say, lower-end markets. And this is not to say that it doesn't serve a purpose because it's so-called lower-end. It has different set of requirements. But out of that came what we call TSN, time-sensitive networks. And there are a number of profiles that are being defined for different industries based on that specification. Industrial automation, so this is quite simply replacing systems from 40, 50, 60 years ago, which would actually, control industrial plants with something slightly more modern than 2 wires with Ethernet. Financial markets, I mentioned before, high-frequency trading and that sort of likes. And then the last one is the data center one, which is the OCP profile, which I also help co-author. So the last couple of slides are about the use case in terms of network design for the OCP model. So the reference layer, timing reference layer at the top is obviously going to use what we saw on previous slides, which is a reference clock. You're going to discipline a grandmaster, which in OCP lingo is the open time server. There's also a other project there related to building out of open sourced information and design boards that allow you to run as grandmasters. Great weekend project for anyone who wants to play with this. And then, of course, in the middle, you've got a network fabric, which will have n number of layers depending on the size of your data centers, the number of hosts, and your architecture, and whatever else. In the OCP model, they use transparent clocks. Okay? So that's the main purpose in order to make sure that, in theory, all packets are going to be symmetrical and go through the same path. They want to avoid problems related to spraying of traffic or whatever. So they've actually decided that they want to have TCs because it makes it slightly easier in some of the models. I also believe, and this is my personal point of view, is that there is misunderstanding on what modern boundary clocks can do, but that's a conversation over a beer or a coffee or something else. The server layer, obviously, you've got a very wide set of servers, which then have the applications we were talking about, and the hardware timestamping at that layer. I will leave this as a reference, which you can go look in the details and run the maths on it if you really want to, but it explains more or less that from a reference clock at the top, you want to be within 100 nanoseconds of something we call TAI, which in French is Temps Atomique International, or International Atomic Time, which is your UTC time minus the leap seconds, okay? And at the bottom of the stack, you want to be less than 2.5 microseconds away from that reference because that's what they believe is the current required target in order to achieve the performance for the use cases that were mentioned before. And again, another reference slide, since I know I'm running out of time, is around what are the key values. So those who know about PTP will understand most of what's on here. Ultimately, it's saying IPv6 is the default. It's mandatory. We're using transparent clock. These are the message rates at which we're running. The communication is unicast because they believe there's no multicast in most data centers, and I think they're quite right. And there are different clock classes and there are different failover algorithms for selecting who's the current grandmaster. So, in conclusion, the nanosecond scale world is fascinating. You discover so many things happening at that very microgranular level in terms of problems and how systems operate, which you obviously don't see when you're running systems at a let's say, a wider scale in terms of less accurate, I mean. It builds on existing spec, which is now 20 years old and has been revised multiple times. It has been tuned for data center applications through the Open Compute project via the TAP. There's a new set of applications that can be built. There are others that can be improved. But I think that the point right now where we are is you can deliver a reliable time service in a data center as a managed service. But at the same time, there's a learning curve for the software folks to see how they can benefit and how they can consume this. And a lot of discussions I have about is, this sounds great, but what do I do with it? So there's a bit of homework for everybody who's interested in this to see how different use cases and applications can benefit from it. And that's me.
Thank you very much, Thomas. We have time for one question, I'm afraid, only. So, does someone have a question?
Greg?
Thomas, you mentioned quality of oscillators. Do you know any public resources to?
So the OCP has a work stream working on defining oscillator qualities and referencing them for different types of applications and use cases. I wouldn't say that I'm aware of vendors specifically being very open about what is the oscillator they use in their switches or routers or whatever. That might be something under vendor NDA, but in the open community side, there is an effort to qualify the different requirements and what are the different performances you can have out of different generations of oscillator.
Thank you.
You're welcome.
Okay, thank you very much, Thomas.